Swayam Prabha. Digital India. Educated India.
Welcome to the fifth module. In this module, now we shall discuss about the wire additive manufacturing. So, in the first lecture today, we shall give the classification of the wire additive manufacturing processes. Then we shall discuss the most popular additive manufacturing process, which is also called as fuse deposition modeling. In the fuse deposition modeling, we are going to discuss about these topics. We shall discuss about the feeding mechanism of wire. We shall discuss about the pinch roller mechanism, the power required to push the wire into the liquefier and the liquefier dynamics. So, all these phenomena we will be able to cover in the first lecture, and in the second lecture related to FDM, we shall discuss about the die swelling phenomena and bead cooling, the bead deposition, spreading and its bonding, and finally the surface roughness we usually obtain in FDM process. So, the wire based additive manufacturing can also be classified the way we have classified the other additive manufacturing processes based on the subsystem level. So, for example, what kind of materials can be used in the form of wire in additive manufacturing? The wires can be of polymer or of composites. The wires can be of wax or the wire can be of metal. There could be few more if you want to add further. Now, the next is in what way we are transferring the material, whether it is a continuous transformation of the material or that material is getting transferred onto the substrate based on the demand, meaning to say drop on demand. So, for example, this is the wire coming and it is getting melted somehow in a liquefier, and then it is generating the drops. Now, based on the drops generating here, the drop by drop material will be transferred on the substrate. While in the case of continuous, the wire itself get melted onto the substrate. So, the wire keeps on coming out of the nozzle continuously in that case, not like in drops. Also, as in the case of wire based additive manufacturing processes, the support mechanism is not inherent. Like we have seen already in the case of the liquid based additive manufacturing, the liquid material available under the overhanging region, we used to cure it to create the support structures. Also, we have seen in some processes, we add a separate material for the support generation, such as wax in the case of solid ground curing, or jelly like material in the case of objet polyjet. Also, we have seen in the case of sheet based additive manufacturing, the remaining portion of the sheet act as a support material, which later on removes by utilizing the decubing operation. In the case of now wire based additive manufacturing, we have to utilize another material to deposit the support selectively in the desired region. However, the only way to avoid the requirement of support mechanism is by tilting the substrate or the deposition nozzle appropriately so that you can create the part in variable direction. Due to that, the machine tool kinematics also becomes quite complicated. Also, it has been found that the part we used to create by the wire additive manufacturing are huge in size. Due to that, we use different type of kinematics to take the advantages for the build envelope. So, the build kinematics or the machine kinematics can be in the form of serial kinematics, or it can be the parallel kinematics of the machine, or it can be a hybrid kinematics. I will consider the example for each. What is the energy source required to melt the wire? If you are using the material like polymer, composite, wax or any low melting point wire, then of course the resistance heating can help us. If we are using the metal like wires, those responds to the induction heating, where induction heating can be used to melt the wire or to transfer the heat to the wire. Also, we can see the analogy of welding, where arc is used to melt the wire. Either the arc is generated by the consumable electrode or the arc is generated by a non-consumable electrode and wire is fed into it. So, arc can be one very good medium of the energy source to melt the wire. Also, the energy source can be in the form of energy beam. The energy beam could be laser beam or it could be electron beam. As I already discussed briefly, the support mechanism in the case of wire based additive manufacturing could be the following three types. The first is the water dissolvable support. This is more popular in the case of polymers, as we deposit the main material with high density and the support material with low density, so that the support material can be dissolved into the water. Sometimes the support material is also of another material itself, so that it is easily dissolvable into the water. But if you are using metal, this type of water dissolvable support may not work. So, in that case, usually we used to have metal 1, for example stainless steel, and the support is provided by metal 2, that is nothing but assume it copper. So, if stainless steel is deposited and copper is as a support material used, if I do the acid bath of this, I mean I dip the whole thing into HNO3, then copper will get dissolved and it will leave the stainless steel behind. Some of the work has been done to explore this type of acid bath support removal mechanism also. However, as I already explained, if you do not want any support, then of course we have to use multi-axis kinematics. The utilization of multi-axis kinematics can be to tilt the part appropriately while building it, so that the overhanging features can be realized in the variable build direction. So, based on these subcomponents and the different options available for that, you can further classify these processes. So, let me now consider the case when the material is polymer or composite and the material flows continuously out of the nozzle. The machine tool kinematics is the serial kinematics. Serial kinematic means the links are connected one over another like this. So, this is an example of serial kinematics. Then the energy source is resistance heating. Resistance heating is used to melt the wire, and then the support mechanism is water dissolvable, meaning the support which we are depositing here is easily dissolvable into the water. So, such a system which is very popular and you have definitely might have used it already is called as FDM by Stratasys, and the generic name could be fused filament fabrication. So, the FDM process can start like other additive manufacturing process by creation of the CAD model. Then this CAD model is getting converted to the STL file. Then this STL file is oriented in such a way that we considered all the benefits out of the FDM process, and in this case we just keep in mind the DFM rules, the design for additive manufacturing rules, so that you can make it very efficiently utilizing the process. After appropriately orienting the STL file, the supports are generated, and along with the support the entire part is sliced. Each slice used to have the contours corresponding to the support and corresponding to the main material, and then area filling tool path is generated corresponding to both of such regions. After generating the area filling tool path, the G code file is generated which used to transfer to the CNC machine. So, this entire process is called as pre-processing. Then the build process starts. The first step of the build process is the deposition of some buffer layers on the bottom, so that on the substrate or on the build platform where you are building the part, the deposited material can stick properly. So we deposit some buffer layers here. It is also important to deposit the buffer layer sometime. It gives you the large area adhered to the substrate, so that you can build your part efficiently, and during the build the part will not move here and there on the build plate. Then the next step in the build process is the deposition of main material and support material. Wherever required, we deposit the main material, and wherever required, we deposit the support material by utilizing two different nozzles in this case. So usually there are two extruders, let me call it as E1 and let me call it as E2. So this is transferring the main material and this is transferring the support material. Wherever required, for example, you are building this slice in which this region required the main material and this is the portion which requires the support material, which is going to support the overhanging feature which will come above somewhere. So to add material in this region, extruder 1 will be used, and to add material in this region, extruder 2 will be used. These two major steps used in the build process can realize the entire part, and this process is called as build process. The next is the post processing. After completion of the deposition of all the layers into the part, we take the part out of the substrate and then go for the removal of support. The support is usually removed by the technology called as waterworks developed by Stratasys. In that case, the support material, which is of different material, get dissolved into the water easily. The water usually is also mixed with some soap and it is vibrate with ultrasonic vibration. Over a period of time, the support material got eaten away into the solution and it leaves the main material behind. After completion of the removal of the support, the part used to get finished, and this can be done by the grinders or some other chemical methods as well. So this is the process steps involved in a typical FDM process, or also generically called as fused filament fabrication. This video by Solid Concepts can explain the process nicely further. There are two reels on the bottom side, you can see they are going to supply the main material and the support material to the liquefiers. The main material here is in the black color and the model material and the support material is in the white color. The wire get transferred to the liquefiers where they got heated up and get melted. The solid portion of the wire acts as a piston and pushes the molten material through the tiny orifice. Of course, wherever required, the support is deposited. Like you can see here, the overhang is supported by the white color support. Also, it can be noticed the support material is of low density, so that we can save material, and also the removal of the support will be easier. The process repeats itself and build the entire part, and then we take the substrate out and remove the part from the substrate easily. As much as possible, we remove the support by using the mechanical tools, and later on we put the component into the waterworks where the support material is eaten away, and after that we give a finishing touch to the final parts, such as by the grinding and some chemical processes, and create the final finished part. So this is the basics of the FDM or fused filament fabrication process. This additive manufacturing process is the most exploited additive manufacturing process in the world. This is the process which is also available with a very cheaper rate as well. Now let us try to understand, if you want to build this machine of your own, what are the parameters you need to consider and what are the different types of subsystems involved in this machine. Like you are seeing here the machine architecture for particularly FDM or fused filament fabrication process. It is involved of three subsystems mainly. The first one is shown here in the red color. This is the mechanism which pushes the wire into the liquefier. Typically, a pinch roller mechanism is used to feed the filament or the wire into the liquefier. Then after that, this wire which is in the solid form right now, I am writing here solid also. This wire is in solid form, enters into a liquefier. So liquefier is nothing but a chamber which is covered from the surrounding by the heating wires. The wire get the resistance heating and they transfer the heat to the wire and the wire get melted. This chamber is also called as liquefier. So this solid wire here, assume that it is still solid when it is entering into the liquefier, gets melted when it goes down further. So assume that it is melted here. Now this solid wire acts as a piston and pushes this molten region of the wire through a very tiny orifice. So this is the orifice. Of course, to push the wire from a tiny orifice as compared to the entering area, you require to add some additional force from the top. Once the molten material extruded out of the nozzle, it got deposited on a substrate. And this is the third subsystem or the third module of the machine, which is nothing but the relative motion between the substrate and the deposition nozzle. It usually consisted of three motions, the XY motion and the Z motion. The XY motion is required to deposit the material in the XY plane to fill the area and add the material wherever required. The Z motion is required after completion of each layer. When this part will be fabricated in a certain Z height, the entire platform will go down and the next layer will be deposited. Now let us try to understand how this pinch roller mechanism and this liquefier works efficiently to extrude the material or the polymer material through a tiny orifice. So typical feedstock, as already mentioned, are amorphous thermoplastic polymer filaments with a diameter of around 1.5 to 3 millimeter in the case of FDM. In the case of smaller scale machines, these filaments are available as a loose coil. But if you go for a sophisticated system, these filaments are available as a cartridge and you can just replace the cartridge and put it back like you put it in your conventional 2D printer. In either case, of course, the filament is pushed through the system using a pinch roller mechanism like it is illustrated here in this diagram, and one of the pinch roller is attached with a stepper motor. Assume that this one is connected with a stepper motor. When this particular roller rolls, due to the friction acting onto the wire will get pushed down. Typical material used for these rollers are hyphalon or polyurethane. Sometimes one or both rollers have a grooved or toothed surface like gear to create sufficient friction for the roller to grab the filament and feed it to the liquefier without any slippage. The pressure on the filament between the roller is typically sufficient to slightly deform the filament so that the contact area can increase, but it should not increase beyond a certain value, because after that it may also crush the wire, and if the wire is crushed, you will find some marks on the periphery of the wire when it gets pinched into the liquefier. So typically a system of pinch roller looks like this. Here you can see there are two rollers. This is roller 1 and this is roller 2. Let me write the number also, roller 1 and roller 2. These rollers are having a grooved structure here. The groove is used to increase the contact area between the wire and the roller, because if the contact area will increase, of course the friction will increase. And typically a roller is shown here in the zoomed figure. It has a grooved surface here, right, which will be able to accommodate the wire. Now why two rollers are used here? Because we have two material, one for building and another for supporting. This one is the drive gear, and these two rollers, roller 1 and roller 2, are pressed against each other by utilizing a spring. So if someone wants to unlock, he has to just remove this spring from here, and this assembly will be loose with the drive gear. As a result, you will be able to change your main material or support material whatever required. Now of course here in this particular mechanism, if the gear drive is rotating in this direction, it will push this support material, and if it will move in this direction, it will push the main material into the liquefier. So this particular arrangement is typically for the case when both the materials, main and support material, are available with the system. But if you are trying to develop a low cost system, only one material may be sufficient. And if you are using one material, of course you have to be very careful when you deposit the material corresponding to the support, because in that case the material may not be easily removed by the waterworks, because both the materials are same. Hence you cannot use a material which is different from the main material. Therefore in that case you used to deposit the support structure with a very low density area filling strategy, so that by utilizing the mechanical tools I will be able to break these supports easily. However, this is a typical system in the real life of the similar kind. As you see here, this is the spring which I just shown here in the CAD model, and this is the driving gear, and there are two rollers corresponding to the two material. This is roller 1 and this is roller 2, and the wire is pinched into the liquefier. Let me call this liquefier 1 and this is liquefier 2. Also, as you can see here, a typical pinch roller system in the zoom view. Here the pressure between the two rollers is so high that it is crushing the filament in between itself, and this crushing has to be avoided, but on the same time we need to apply the sufficient pressure between the filament and the roller so that we are easily able to push it into the liquefier. So typically in the case of a pinch roller system, as you are seeing here, the wire, this is the filament or wire, it is in tension above, meaning to say, for example, this is the coil, it is having some filler material like this, and it is getting pushed here. Now if I am pulling this wire from this or unwinding this wire from a coil, then definitely there will be a tension force into the wire if I cut anywhere, because I am pulling it. So at any cross section, if I draw the force, it will be in tension. Further, when the wire is pushed beyond the pinch roller mechanism, it is going to enter into the liquefier. As in the case of liquefier, the exit orifice is very tiny, it's very small, right? We need to apply some additional force from the top to push this wire into this tiny orifice. To push this wire into this tiny orifice, a compressive force is typically applied. So the wire will be in compression in the bottom side. So if you look broadly, you will find that the wire on the top is applied with the tension, and wire on the bottom is subjected to a compressive load. So as broadly if you see, the wire at the top is subjected to a tension load, and wire at the bottom is subjected to a compression load. How much this force is F2, that we will discuss after some time. Let us now assume that if the material which is coming out of this tiny orifice is depositing a bead, and the bead is in a rectangular shape, the cross section of the bead is rectangular, assume that, and the thickness of the deposited bead is T and the width is W. Therefore, the cross section area of the deposited bead will be W into T. T. Now if I want to find out the mass flow rate or the deposition rate, I can just multiply this area by the velocity by which I am travelling. This is the traverse velocity. Hence, as a result, the volumetric flow rate Q will be equals to Vt omega T. Also, it can be noticed that the wire which is coming from here, assume that the wire is coming from here, is having a velocity of Vf. This is the velocity of the filament, that is why I am writing Vf. And also the diameter of the wire at this location is df. This is the diameter of the wire. So in that case, I can again find out the volume flow rate, and this volume flow rate will be equals to Q equals to Vf, velocity of the filament, multiplied by the cross section area of the wire, that will be pi by 4 df square. Therefore, I can find out Vf equals to 4Q divided by pi df square as written here in this equation 2. But a correction factor Kf has been added here. So what is Kf? So this correction factor, which is also called as friction factor between the rollers, can have three types of value. The Kf can be greater than 1. Kf will be greater than 1, then the velocity will be greater than the predicted one. This is because when the rollers are crushing the wire, meaning to say they are reducing its diameter also. They are not just applying sufficient pressure in the elastic range, they are plastically deforming it or crushing it. In that case, the area of the wire will reduce. As a result, you will have higher velocity of the wire. As the velocity will be higher, this correction factor or the friction factor's value Kf will be greater than 1. Also, if there is a slip, for example, this is the roller, it is getting slipped between, if for example, this is a roller and due to the insufficient amount of friction between the wire and the rollers are getting slipped. In that case, you will not get the exact same velocity of the wire which is transferred by the rollers due to its angular velocity. As a result, Vf will be less than the predicted one, and this will be accommodated by this friction factor Kf. Kf will be 0 if we are ideally feeding the wire without crushing it or without slipping the roller against the wire. That is why our formula for velocity of the wire or the filament velocity has been modified by accommodating this friction coefficient as Kf into 4Q divided by pi df square. Also, the velocity of this filament can be obtained by the rotation of these rollers. So if these rollers are rotating with the angular velocity of omega r and the diameter of the roller is dr, then the velocity of this any point on the periphery of these rollers will be equals to V equals to r, that is nothing but dr by 2 into omega r. If you assume that there is no slip between the roller and the wire, then the velocity of wire will be also equals to this value, and hence your Vf will be equals to omega r dr by 2. Hence I can put this value here. As a result, I will have omega r dr by 2 equals to Kf 4. Now this Q, I can replace this Q by the deposition rate or the volume rate we were calculating at the exit of the nozzle, because the input to the nozzle and the exit to the nozzle, the volume flow rate should be same, and we have calculated at the exit the volume flow rate was Vt, that is the traverse velocity, into width of the deposited bead into thickness of the deposited bead. So I am writing here Vt W into T divided by pi df square. Now from this equation I can easily find out the required omega r, that is the angular velocity of the rollers, and hence it will be equals to this. Omega r will be equals to 8 kf Vt by pi dr df. So this is the input. Because I am rotating my motor with some finite value of rpm, and therefore now I can have the relationship between the angular velocity of the roller, that is omega r, with the other process parameters. We can observe very fundamental things from here, like if you want to increase the thickness of the deposition bead or the deposited bead, you have to rotate with a higher rpm. If you want to even deposit higher width, again you have to increase the rpm. Also, if the travel velocity is increasing, then for that also you need to keep the other parameters same, like w and t same, you have to increase the value of omega r, that is the speed of the rollers. Also, if the diameter of the roller is reducing, then in that case the roller should rotate with a higher speed. It can be also seen that if the diameter of wire is reducing, again to maintain the same value of w, t and vt, you need to increase the value of omega r. So I have now many controls in my hand when I am feeding these wires into the liquefier. By just controlling the value of omega r, I can control several other parameters. Now let us discuss about the force required to push the wire into the liquefier. It is important to calculate the value of F2, because if you want to select the appropriate motor for feeding the wire into the liquefier, we need to calculate the power. And we know that power is nothing but the torque into omega, and torque will be calculated by the force into radius. Force acting maybe this F2 into this radius r. Now to find out this value of F, there are two F required. One, to unwind the wire from the reel or the filament reel, and another is the force required to push the wire into the liquefier. The force required to unwind the wire from the reel can be neglected because it may not be required in a very large extent, but the force required to push the wire into the liquefier will be really quite high. So how can we calculate this force? Assume that to push the wire from this end to this end, the pressure drop in the liquefier is represented by delta P, and hence the force F2 will be equals to delta P into pi df square by 4, where df is nothing but the diameter of the filament, and we are assuming that the opening of this nozzle is also almost equal to the diameter of the filament. Now assume that only one of these motor is running. Assume that this motor is just nothing, it is not running, but it is just acting as an idler. So this is the driver and this is just the idler, and they are definitely connected with some spring to apply appropriate force against the wire. Now if the motor is rotating, the required torque will be T, and that torque required will be equals to the force required to push this wire against the liquefier multiplied by the radius of the roller, that is nothing but dr by 2. We have already seen that F2 will be equals to pi df square by 4 into delta P. Hence I am writing the torque required to push the wire into the liquefier will be equals to pi by 8 delta P into dr df square. Now let us find out the power required. Of course, the power required for the motor will be equals to the torque required into the angular velocity of the motor or the rollers. So it will be T2 into omega r. Now if it is T2 into omega r, I can put the value of omega r which we have derived just now, and it was omega r equals to 8 kf Vt Wt divided by dr df square. So as dr and df square will be cancelled out, as a result, and this 8 will also get cancelled out, and also there is a pi here, this pi will also get cancelled out. You will have the final value for power equals to kf delta p Vt into Wt. We know that this Vt Wt is nothing but the flow rate, and this flow rate can also be calculated from the feeding of the wire, and in that case it will be nothing but the velocity of the feed or the velocity of the filament Vf into pi by 4 df square. So any one of these values can be kept here. As I have already mentioned, the force required for unwinding the filament from the reel has been neglected in this case. So now the question comes, how to find out this delta P, because other parameters are known to me. Also, it is very important now to find out what can be the maximum value of this F2, because there are going to be some issues in this particular zone. So what will happen? When we are applying a compression load here, right, it may happen that the wire may buckle at this location. So the compression on the liquefier side of the feed roller places a limit on the Q or the flow rate Q. Why so? Because when this compression reaches a critical limit, the feedstock filament can buckle like shown here. And it is the most common failure in most of the FDM machines. You might have seen that also. The wire keeps on coming out and it got crumbled near to the pinch rollers. You have seen already that. And the major reason behind that is the buckling of the wire. Now let us try to find out the value of the critical load which can be applied on the wire between the pinch roller and entry point into the liquefier. This value we know that should not exceed the value beyond which the buckling may occur in the column of the wire shown here. So for that we already know that the buckling load, if it is applied for different end condition of the column, different critical value of the buckling load can be obtained. Like for the column which is pinned from both the end, the value of the critical buckling load is pi square EI by L square, where L is the effective length. Then in other case, if the column is fixed from both the ends, then the critical value of the buckling load is 4 pi square EI divided by L square, where the effective length in this case will be equals to 0.5 L, this region, that is the 0.5 L. In a similar condition, for different end conditions, the value of the critical buckling load is given here in this chart. Now in our case, as we have this wire attached with the rollers and it is entering into the liquefier here, we can assume that this is a condition of pin column. So both the end we can consider as the pin joints. Now if it is considered, then the critical value of the buckling load will be given by this formula, that is pi square EI by L square, where effective length is also L, means from here to here the entire length is the effective length. Then in that case, let me write this formula here again, and it will look like F equals to pi square EI by L square, where L is the second moment of inertia of the cross section of the wire which we are considering here. And of course we know that the cross section of the wire is nothing but a circle. Therefore, and the minimum second moment of inertia will be I equals to pi d to the power 4 divided by 64, where d is nothing but the diameter of the wire or the filament. Now replacing this value here, we will obtain the value of F as pi cube E df to the power 4 divided by 64 L square, where df I am writing corresponding to the diameter of filament. Again, if I just divide this value of F, means this force F2 acting on the wire divided by the cross section area of the wire, then I will have the stress acting on that or the load acting on the wire. Then it will give me the stress acting on the wire, and that will be equals to F divided by pi by 4 dF square. As a result, the right side term will also change. Therefore, I can say that this is the value corresponding to the maximum pressure which the wire can handle if we are pushing it towards the liquefier. Therefore, the pressure into the liquefier, which I am saying right now maybe delta P, should not exceed this value. If it is exceeding this value, then definitely the wire get buckled in this region. Also, we know that the diameter of the liquefier will be slightly larger than the diameter of the wire. Therefore, to accommodate this error, usually a correction factor of 1.1 is used, and the modified value of the pressure which the wire can handle can be given as P2Cr, the critical pressure acting on the wire, equals to 1.1 multiplied by pi square E dF square divided by 16 LF square. Here again I am replacing this L with LF because I am talking particularly about this distance, that is LF right now. So now we have obtained the critical value of the pressure which the wire can handle between the pinch roller and the liquefier. This pressure will depend on how much pressure is required to pass this wire through the liquefier. As there will be a pressure drop, of course, when the wire will enter into the liquefier, we have to find out this pressure drop. So for that, let us try to understand the liquefier dynamics. So liquefier or the print head is the part of the machine where the solid polymer stock is melted and pushed through the small print nozzle. Usually, this is the typical schematic of the liquefier, which is nothing but this particular thing. I am just zooming it out later on here in this image. It is divided into 3 zones: zone 1, zone 2 and zone 3. Zone 1 is the initial region where there are heating coils. So assume that these are the heating coils. In this region, the wire get melted. In the beginning, of course, the wire is in the solid state form, and then when it goes downward, it got melted. After some time, when the wire is almost melted at the end of this region 1, now the diameter of the wire we start to reduce. In the zone 2, which is typically of a conical form like you are seeing here. As the wire is in the molten form, of course, this top solid form of the wire will act as a piston and it will push the molten material downwards like this. As a result, your molten material will flow and its diameter will change. Later on, at the end of the region 2, the diameter of the molten material flowing inside the nozzle will be equals to diameter of the opening, that is D2. Then after that, it will flow through this length D2, that is corresponding to the region 3, and the molten material will come out or extruded out from the nozzle. However, the dynamics of liquefier is quite complex and challenging to model as melt properties are a non-linear function of temperature and shear rate. However, the force required to extrude the melt must be sufficient to overcome the pressure drop across the system, which strictly depend on the viscous property of the same melt as well as the geometry of the liquefied nozzle. The geometric parameters are typically this length L1 and the opening diameter where the solid wire is entering into it, that is D1. Then of course the cone angle beta and the exit diameter D2 and the exit length L2. Of course, if there is a large difference between D1 and D2, more pressure will be required. Therefore, we will try to find out the force required to extrude the melt sufficient enough just to cross this melt out of this nozzle, and that will be the minimum pressure required, and that I will represent by delta P. because of the fact that the melts adhere to the liquefied dye's wall. So, this is the wall of the dye, liquid metal will adhere to this, right, because this particular layer will adhere like this. And of course, the molten material will be subjected to the shear deformation during the flow, right. This will be at the stationary assume, and the remaining material at the towards the center will shear out and flow towards the nozzle's opening. So, the determination of this shear rate can be given by this formula. So, the shear rate will be equals to minus dV by dr, where V is the velocity of the melt and r is the radius of the liquefier. The thermoplastic typically used in the FDM usually exhibit the shear thinning behavior. That is, the viscosity decreases when we increase the shear rate. It can be assumed that adopting a power law for generalized Newtonian fluid for modeling of polymers such as ABS is sufficiently accurate for modeling of FDM melts. So, the power law can be defined like this. It says the shear stress tau will be equals to the shear stress rate gamma dot divided by the fluidity phi. Fluidity is nothing but the reciprocal of the viscosity to the power 1 upon m, where m is nothing but the flow exponent. The general flow characteristic of a material and its deviation from Newtonian behavior is reflected by the flow exponent nothing but m. So, as you can see, if the value of m is 1, of course, it will be a Newtonian fluid, and based on the value of m, it can be either pseudoplastic material or it can be dilatant material like this. So, if it is a pseudoplastic material, of course, the value of m will be greater than 1. If it is pseudoplastic material, of course, the value of m will be greater than 1, and that is the case for the usually used melts in the FDM process. Now, let us try to find out the pressure drop which will occur when the molten plastic material will flow through this liquefier. So, usually by applying the power law to the moment flux balance on the fluid element respectively in the zone 1, zone 2 and zone 3, one can find out the pressure drop. I am not going into the detail of how this pressure drop can be obtained, but the interested students may refer to this particular book, which is particularly for designing the injection molds. So, it is the extrusion die for plastic and rubber design and engineering computation. From this book, I have obtained that the pressure difference in the zone 1 required to push the wire will be equals to 2L1, that is the length of zone 1, V, which is the velocity of the wire or the melt into the nozzle, divided by phi to the power 1 upon m, bracket 1 plus 3 divided by d1 by 2 to the power m plus 1 to the power 1 upon m. In a similar fashion, the pressure drop in zone 3 will be equals to delta P3 equals to 2L2 V divided by phi to the power 1 upon m, bracket m plus 3 d1 by 2 to the power 2 d2 by 2 to the power m plus 3 to the power 1 upon m, where V is nothing but the velocity of the wire which is entering into the nozzle, and L2 is corresponding to the length of the zone 3. D2 is the diameter of the zone 3, and other values like m is the flow exponent and phi is the fluidity. Also, the pressure drop in the zone 2, which is not straight like zone 1 and zone 2, it is having a conical region, will be given as delta P2 equals to 2m divided by 310 beta by 2 bracket 1 upon d to the power 3 by m minus 1 upon d1 to the power 3 by m, bracket d1 by 2 square into m plus 3 into 2 to the power m plus 3 to the power 1 upon m. So, by utilizing these formulas, we can predict the pressure drop required in zone 1, in zone 2 and zone 3. It can be noticed while obtaining these pressure drops in different regions like region 1, 2 and 3, we have assumed that the temperature of the melt is constant. That means these pressure drops can be applicable only in the steady state. What happened when we start the process or we increase the speed in between? For that we have to consider the condition where the temperature will be different at different location. So, as this particular pressure drop is applicable only when the isothermal condition has been assumed throughout the melt, that means it is applicable only in the steady state. And of course, to obtain the total pressure drop required to push the wire through this liquefier will be delta P equals to delta P1 plus delta P2 plus delta P3. Now, it can be easily obtained also by utilizing these formulas. So, like I have mentioned in our previous consideration, we have assumed that the temperature of the melt is everywhere same in the liquefier and which is equal to the deposition temperature. But when a sudden change in the flow rate is applied, for example, you are suddenly increasing the speed. For example, this is the wire and you are suddenly increasing the speed. Earlier it was V1 and now you are increasing it to V2. So, what will happen? There will be some more portion in the region which will having some temperature T1 less than the later or the earlier temperature T0. With the introduction of new material in the system, the average velocity of the fluid will also increase because now this velocity V2 is there and earlier it was the average velocity was V1 or V. Now the average velocity will be V plus V2 by 2. So the average velocity, this is approximate calculation I am doing, will increase in the entire region. So in order to stabilize the new steady state condition, the heat must flow, right? You have to quickly add more heat from these heaters which is aligned towards the region 1. So how much should be this heat first of all? Now in order to stabilize the new steady state condition, the heat flow must be increased. If the heat flow will increase, definitely this temperature which is lower than the earlier temperature T0 will become equal and we will be having the or we will be able to maintain the steady state condition. However, as this process is done by taking the feedback from the thermocouple attached here, there is always a delay. This cannot happen all of a sudden. Therefore, there will be a huge pressure drop required to push the molten material through this liquefier when you change the velocity from V1 to V2 suddenly. Now, let us first see what will be the value of the heat input required to manage this temperature and to maintain the steady state condition. The temperature is regulated via heat input through these coils, right, as I have already mentioned, and these coils are usually attached only along the region 1. The system continuously adjusts the power supply to these coils according to the temperature difference into the liquefier. And how do we obtain the value of this temperature difference? Through the thermocouples. The response time of the temperature controlling loop is thus in order of like seconds. It takes few seconds to control the temperature inside the liquefier if there is any sudden change. So during the time of thermal adjustment, the flow is non-isothermal. Okay, we cannot consider the flow into the melt as isothermal during this adjustment period. So due to the delay which is coming because of the thermocouple reading that is giving feedback to the heater, the delay is typically of a range of second. This delay, during this delay, the flow will not be having the same temperature into the liquefier. Therefore, we cannot consider the isothermal conditions which we have assumed earlier. However, we will try to give the heat as soon as possible so that we can maintain this temperature. So, during the time of thermal adjustment, the flow is non-isothermal. So, temperature dependence of the viscosity must be taken into the account along with the shear stress rate dependency. The necessary heat flow rate which is supplied through the wall of the liquefier can be approximately determined by this formula. So, it says the heat required to increase the temperature delta T will be equals to, which is nothing but the initial temperature and the difference of the new temperature into the mass flow rate into the liquefier into the specific heat capacity, that is Cp. Now, this mass flow rate can be obtained by rho Va, that is the cross section of the liquefier in the first zone, into the velocity, average velocity of the melt, into the density. Also, the area from which we are supplying the heat is given here. So, this is the surface area, right, because these coils are like this, right, these coils are surrounded into the region 1. So, the area corresponding to the heat input, I am writing it as AH, will be equals to pi D1, that is the diameter of this zone D1, into the length of this zone L1. Therefore, the heat flow rate can be given as Q divided by AH, and hence your heat flow rate Q will be equals to T minus Ti rho Va Cp divided by pi D1 L1, where Ti is the initial temperature of the melt into the liquefier and T is the new temperature which is obtained from the thermocouples reading after there is a change into the velocity or in the beginning or end of the process. So, as I have already mentioned, during the time of thermal adjustment, the flow is non-isothermal. So, temperature dependence of viscosity must be taken into the account along with the shear rate dependency. Thus, the viscosity will be modified. Now, the viscosity will not be only a function of the strain rate that was assumed earlier, but it will be a function of the temperature also into the melt or into the liquefier, where HT is account for temperature dependence, and like I mentioned, N naught gamma dot is the expression for viscosity at the same reference temperature T alpha, at which the value of m and phi was taken in the beginning. Now, of course, this function HT can be given as exponential alpha 1 upon T minus 1 upon T alpha. This is also called as Arrhenius relation. At reference temperature where HT is equals to 1. So, let us accommodate this temperature dependent terms also into our pressure difference, and as a result we will have the value of the pressure drop in region 1 as the same relation which we derived earlier for the isothermal into exponential alpha 1 upon T minus 1 upon T alpha, where T alpha is nothing but the temperature at which we have considered this value of m and phi. In a similar fashion, the pressure drop in other regions like in region 2 and region 3 will also get modified, and an additional term will be there now, exponential alpha 1 upon T minus 1 upon T alpha. Now, it can be observed that when a sudden change in the flow rate occur, the average temperature T drops and velocity V increases, right, because in the liquefier if there is a sudden change, the average velocity will increase because you are increasing the velocity. The average velocity into the liquefier is now increasing, therefore, this value is increasing, right. Also, as suddenly there is a new material entering into the liquefier, this temperature, the average temperature will decrease. As this value of T will decrease, this value of 1 upon T will increase. As a result, this exponential 1 upon T, this whole term will increase exponentially. So, due to the fact of increasing the velocity, the average velocity, and also the decrease of the temperature, and hence increasing the term exponential 1 upon T, the pressure drop will suddenly increase with a very high value, and that is why the phenomena of the wire buckling usually occur in the beginning of the process or when you are changing the wire speed without changing the heat input to the liquefier. So, whatever the condition is, if it is the isothermal or non-isothermal, the total pressure drop into the liquefier can be given as delta P equals to delta P1 plus delta P2 plus delta P3. Now, we can easily find out the motor power because it was already now known to us that what is the value of delta P. Let us now consider an example for FDM. So, it is given that in an FDM process, a wire of diameter 1.5 mm is used. The wire is fed with a velocity of 0.86 mm per second and the area of bead deposited is 0.88 mm square. What should be the nozzle travel speed if there is no slip between the pinch roller and the wire? If there is no slip, of course, the value of this Kf will be 1. The diameter of the wire means the value of dF is given to us. The wire feed speed is given, that means Vf is also given to us, and also the area of the deposited bead is also given to us, and this area is nothing but the W into T. Assume that if you are depositing the rectangular bead, in that case this area A of the deposited bead is given to us. Let us apply the simple mass flow rate conservation here. Q will be equals to the volume flow rate which is coming from the top corresponding to the wire. So, wire is there, this is the wire, it is coming with the velocity of Vf and its cross sectional area is pi by 4 dF square. Therefore, the volume flow rate will be pi by 4 dF square into Vf. Also, the nozzle is travelling with the velocity Vt and depositing the material onto the substrate. Therefore, the volume flow rate which is obtaining on the substrate or the deposited on the substrate can be given as Vt into the area deposited or the cross sectional area of the bead deposited. Therefore, this value will be equals to As, that is the cross sectional area of the bead deposited, into Vt. Hence, you can find out from this equation the value of Vt easily, and the value of Vt is coming to be the required velocity or the traverse velocity will be 0.134 mm per second. Also, now it is asked that if the roller diameter is 16 mm, calculate the roller's angular velocity. So, as we are assuming, it is not given to us that how many rollers are the driving rollers. Assume that there is one roller which is the idler roller and another is the driving roller. So, only one driving roller is there, which they are both connected with a spring and applying sufficient pressure to the wire, but this pressure is just sufficient enough to push the wire without any slip or crushing it. So, the omega r will be equals to the velocity of this wire Vf divided by the radius of the roller, that is r. If the diameter is given to us, of course, it will be dr by 2, and hence omega r will be equals to 2Vf divided by dr. As a result, your angular velocity will be 0.1075 rotation per second. If you want to convert into minute, just multiply it by 60. Now, in the previous question, further it is asked that if the geometry of the liquefier is given here, this is the geometry of the liquefier, where the nozzle diameter which is opening towards the wire which is coming into it, and the diameter of the wire we already know it is 1.5 mm. The nozzle diameter is 2 mm, and then the length of the liquefier where the heating coils are given, that is corresponding to the zone 1, is 100 mm. Then after that, the melt is passing through a conical region number 2, and the value of this cone angle is beta equals to 30 degree. Then the melt is going into the region 3, where the length of the zone is 5 mm and the nozzle opening is only 0.2 mm. Hence, this liquefier is basically doing nothing but extruding the wire which is converting its diameter from 2 mm to 0.2 mm. It is also given that the properties of the melt are m equals to 1.667, that is the flow exponent, and the fluidity phi equals to 0.46. Of course, if m is equals to 1.667, 1 upon m will be 0.6, that will help us in calculating the value quickly. Assume the isothermal condition, means we are considering the steady state when there is no sudden change. In that condition, please note that you will be on the very safe side. The calculations may not be on the safe side, but your assumption is very underestimating the conditions. We have already seen sudden change in the temperature, which is coming due to the sudden change in the velocity, creates a huge pressure difference, because the term exponential 1 upon t will make a big change. But for this particular example, it is asked that the isothermal condition has to be obtained. In that case, we are assuming that the entire melt inside the liquefier is at 140 degrees centigrade. Now it is asked, find out the pressure drop in the liquefier. So the pressure drop in the liquefier will be equals to 2L1 in the zone 1 will be equals to 2L1, the average velocity inside the liquefier divided by fluidity, to the power 1 upon m, that is nothing but the flow exponent, into m plus 3 divided by d1 by 2 to the power m plus 1 to the power 1 upon m. As a result, if I solve this equation just by putting these values, I will get the pressure drop required in zone 1 to be equal to 733.6 Pascal. Similarly, for other zones I have calculated, the pressure drop required in zone 2 is given by this value, and the pressure drop required in the zone 3 is coming to be this value. So the total pressure drop required to pass the melt through this liquefier will be equals to delta P1 plus delta P2 plus delta P3, and as a result you will obtain this value for the pressure drop. Please note that this calculation is for the steady state, not when you are suddenly changing the velocity. We have already discussed, if you suddenly change the velocity, the condition will not remain isothermal inside the melt or inside the liquefier. In that case, the temperature will be less in the beginning of the liquefier and it will be more in the end, and thermocouple will take some time to provide sufficient heat into the melt to bring the isothermal condition back. But during that small period, that is in the seconds, the pressure drop will be suddenly increasing, and due to the sudden increase in the pressure drop, you may exceed the critical value of the pressure which is required to avoid the buckling, and hence you may even face some issues related to buckling in the beginning itself, and you may not get the melt extruded through the nozzle. Now, as we know already the delta P, it is asked what will be the force required to push the wire into the liquefier, that too in the steady state. The F2 force which is acting here to push the wire into the liquefier to overcome this pressure delta P will be equals to delta P into pi dF square by 4, and as a result the value of F2 is coming to be 0.2 Newton. Now again it is asking that determine the maximum possible value of the length LF, this length LF, to avoid the buckling in this zone. It is given that assume E equals to 19 megapascal only. So we know that to avoid the buckling, the pressure required to push the wire into the liquefier delta P should be less than the critical pressure which is possible to apply on this wire. We have already seen this critical value of this pressure will be equals to 1.1 into pi square E dF square divided by 16 LF square, and this value should be greater than the required pressure drop in the liquefier, that is given by this value we just obtained. As a result, we will obtain the value of LF, and it is coming to be that LF should be less than 1.6 meter, meaning to say it is very safe. because it is suggesting that you can go with a very high value of LF. However, please note that again this value of LF we are obtaining for the condition when the melt is at isothermal inside the liquefier, but the pressure drop may be different when you suddenly increase the speed. Therefore, if you are properly designed the system, you have to consider the worst case as well. So with this, thank you very much.